So for lesson 8.5, the remainder and factor theorems, we're going to start off with an example right away. So the first example says, part A, determine the value of f of 3 if f of x is equal to 3x cubed minus 2x squared minus 4x plus 5 by using direct substitution. And please recall that direct substitution is simply when you substitute the value of 3 in for x. Part B is asking to determine the remainder if f of x is divided by the quantity x minus 3. So let's take a look at part A first. This should be pretty simple. So when we say f of 3, we're really saying substitute 3 in where there's an x. Okay, and evaluating this. We're going to have 81 minus 18. It should be minus 12 plus 5. Yep. Okay, which simplifies to give us just simply 56. So again, the value of the function when x equals 3, the function when x equals 3 right here, is equal to simply 56. Okay, 56. For part B, it says to determine the remainder if the quantity or the function f of x that we started with up here was divided by x minus 3. And already you can see some things going on here with the 3's, so let's try and keep that in mind. So that was part A. This is going to be part B down here. Okay. So for part B, we want to go ahead and use our synthetic division process here instead of long division. That would be a mess. So let's do synthetic. We'll make our table. Along the top of our table, put our coefficients, 3, -2, -4, and 5. There's nothing missing up here, so I don't have to worry about any placeholders. I've got cube, squared, linear, constant. After that, I have to remember what goes out here. Well, out here goes whatever you're dividing by, but in the form x minus c. So if it's in the form x minus c, if we think about this in our mind, then c is just 3. They're both the negative, so it's like they cancel in a sense. But the place of c is taken by the number 3. So 3 goes out here now. And we go ahead, we go through the process. Move the 3 down. 3 times 3 is 9. 9 plus -2 is just going to give me 7. Then we have 3 times 7 is 21. 21 plus -4 is going to give me 17. Then we have 3 times 17. That's going to give me 51. 51 plus 5 is going to give me 56. And take a look. There's our remainder. And what do you know? It seems that the remainder that we get when dividing by x minus c is the same as f of c. And let's think about that for a second, right? In this case, we said that c was equal to 3, right? We put this 3 out here. So if you ever have a direct evaluation like this with this number 3, you could also just put that number outside the table. So f of c is equal to whatever the remainder is, right? The remainder in the function f of x is divided by x minus c. That's how I think about this point, right? Think about it again. Let's just reiterate. When evaluating the function at the point c, it's the same thing as dividing the function by the quantity x minus c, and that's what we got here. Now, there's a formal definition of this theorem, and what this is really is the remainder theorem. Okay, it's the remainder theorem. The function at f of c is the same as the remainder when the function f of x is divided by x minus c. A lot of other books and math publications use a process called synthetic substitution. So that's what they call this, because again, this is like direct substitution earlier. For part A, we can call this synthetic substitution. If we want to know the function f of 2 or f of 7 or f of 8, we can just put 2 or 7 or 8 here and substitute it in synthetically. So this is, again, really the remainder theorem. And if you want to see a direct or a formal definition of this, go ahead and take a look at page 372 in your text. They'll give you a proof and a formal definition, but this is really what the remainder theorem is. Okay, the remainder theorem, also known as synthetic, because this was, remember, synthetic division, so now we just title it synthetic substitution. Okay. Quick correction in part A, this should say 81 to give you the correct answer of 56. So the following theorem is a corollary of the remainder theorem. It's called the factor theorem, and it says the following: the polynomial f of x has x minus c as a factor if and only if c is a root of the equation. And we've talked about this many times before. Just to give you a quick example, if you had an equation like this, the roots would be 2 and 4, right? So again, if c is a root, then x minus c is a factor, which is obvious. Here's the root, there's the factor. Well, how does this help us? Well, this helps us actually a lot, because in other words, if the remainder is equal to 0, then c is a root of the equation, and therefore x minus c is a factor. Because remember, if the remainder equals 0, then the function's value is 0, so we must have a root there. And therefore, if c is a root, x minus c is a factor. So we can use our synthetic table to help utilize this factor theorem as well. So this second example says the following: if x plus 4 is a factor of f of x equals x cubed minus 5x squared minus 22x plus 56, then find the other factors. So we have one factor, we want to find the others. Now, based on the other factors, what are the zeros of this function? So we have to think to ourselves, if x plus 4 is a factor, then x equals negative 4 is one of the roots. So if x equals negative 4 is a root, we can go ahead and plug that in here. Let's take a look. Let's plug negative 4 into here. 1, negative 5, negative 22, and 56. Again, x plus 4 is a factor, therefore negative 4 must be a root. We've got that from the last part, from the factor theorem. Now we can bring down our numbers, bring down our 1. We're going to get from this second part negative 9, and multiplying and adding we're going to get 14, and multiplying and adding we're going to get 0. Well, obviously this better be 0, right? This remainder at the end over here has got to be 0, because we said already that x plus 4 was a factor. But this gives me, remember, we have a depressed equation here. And we haven't used that term yet, but it's called a depressed equation, the equation that comes as a result of this. So we end up with x squared minus 9x plus 14. Well, what does that do for us? That tells us that this is one of the other factors of the original equation. So here's what the original equation really is. Or I should say the original function, really. Okay, that's what this is. This up here has become what we have down in red now. But the cool part is that, yeah, x plus 4 is a factor. Now we have the other factor. Because we have the other factor, we can try and factor that using either, standard factoring methods, which is pretty obvious we can do here, or the quadratic formula if we wanted to find the other roots. But for now, we're trying to find the factors, which, those factors are pretty simple. Take a look. X minus 7, x minus 2. It's the only thing that works. And then this is x plus 4. So now what we've got is we've got a factored equation here. X minus 7, x minus 2, x plus 4. Those are our three factors. So given those three factors, the next part says, based on the factors, what are the zeros of this function? Well, it's pretty simple. How do we find zeros of a function? Set it equal to 0. And we remember that when you set a whole equation equal to 0, all of the factors can be equal to 0. So if all of these could equal 0, we solve for each of them. This will become 7, this will become 2, and this will become negative 4. So we have like our t-chart from quadratics this year, but now we have 3 solutions. So our roots of the equation are 7, 2, and negative 4. And it's pretty obvious, right? Because, x plus 4 was a factor, so negative 4 has got to show up as one of our answers there, and that's clear. The other two answers come as a result of this depressed equation. Okay, now we're going to start by saying if we have a root, so if x equals 1 is a root of this equation, 0 equals x cubed minus 4x squared minus 15x plus 18, then find the other roots of this equation. Well, if we have a root already, we can automatically start by putting that root into the function. If we put this root into the function, what we're going to do again is get that depressed equation. What we're doing right now is the same thing as if we were just dividing by the quantity x minus 1. Because when we divide by x minus 1, it's like putting a 1 in the synthetic table. So if we divide by x minus 1, we would get the other factor and then factor that. So that's really what we're doing. It's the same as example 2, just worded differently. So let's bring down a 1. Multiplying and adding, we're going to get negative 3. Multiplying and adding, we're going to get negative 18. Multiplying and adding, we're going to get 0. And again, this has got to be 0 because we're told that this is a root. If we're given a root and we plug that into the table, we should get 0 as a remainder. If we're given a factor and we plug in, the opposite of whatever that factor is, really it looks like, c instead of x minus c, we'll also get 0. So anyhow, the depressed equation becomes x squared minus 3x minus 18. Now, that's the other equation that comes out of this. So what we can do with that is we could say that, all right, well this here, this must be, there's no other possible way, this must be an equation that we could set equal to 0. Because we're told that this was a root earlier, right? This x plus 1 was a root. So therefore, if this is a root, that means that we've now got one of the factors. Right? What's the other factor? Well, the other factor, I'll just write it over here on the side, is x minus 1. That's what this equation really is. This equation that we started with up here, this is what's really going on right now. Okay, but we don't care about this right now. We don't really have to worry too much right now. We have to know that what we got here, this depressed equation, is this other factor. Now we need to set this equal to 0. So ignore this for now. So doing so, we're going to get x minus 6 and x plus 3. Okay, we're ignoring that for now. We already have that root. So this tells me that the depressed equation can factor even further. So having these two factors, we can get our other two roots. Example 4 is a little bit easier actually than all the others because it just says determine if it's a factor. And remember that if x plus 2 is a factor, when we plug in negative 2 into the synthetic table, we should get 0 as the remainder. So that's our check. So again, if this is a factor, it's the same thing as asking determine if x equals negative 2. Okay, it's the same thing as asking this. Determine if x equals negative 2 is a root. It's the exact same thing, okay? A root. So, of the equation, this equals 0 over here, obviously. So let's plug in negative 2 into our table. Across the top, we have 2, negative 4, 1, and 7. Bring it down to 2. Multiplying, adding, we're going to get negative 8. Again, multiplying, adding, we're going to get 17. And then again, multiplying and adding, we're going to get negative 27. So the remainder is negative 27. Remember, a factor is only going to exist if when plugged into the substitution table, or the substitution and synthetic table, we get 0 as a remainder. And clearly here, 0 is not the remainder. So since it's not equal to 0, we could say x plus 2 is not a factor. So two other theorems that we should discuss that are quite important, and they're really coming out of section 8.6 in your book. It says, the first one, every polynomial equation with positive degree n has exactly n roots. So remember, and we talked about this earlier in the year, if you have an equation that says like x to the 5th plus ... equals 0, you're going to have 5 roots. Now, nobody says if they're real or imaginary. That's something that you have to figure out based on the equation, or based on the, in this case, equation. So again, degree indicates the number of roots, The second theorem says if a polynomial equation with real coefficients has a plus bi as a root, then a minus bi is also a root. And we've talked about this already with quadratics, because remember that complex conjugates come in pairs. That's why they're called conjugates. They come in pairs. So for example, if you're solving an equation and you have a quadratic such as x squared plus 2x, that's the second part, plus 2x minus 7 equals 0, it's pretty obvious that you can't factor this equation, so we're going to have to use the quadratic formula, and that's the easiest way to think about this. The quadratic formula shows me the following. it says, okay, well, I can say x equals negative b plus or minus, that's the key there, square root of b squared minus 4 times a times c, it's a negative 7 there, all over 2a. So clearly we can see here, yeah, sure, this is going to be a real answer here, but if we had, say, you know, a positive 7 for c, this would change to a positive 7, which would now make what's under this radical, or would make the discriminant negative, right? This is going to be 4 minus 28. This is definitely going to be a negative number. So we're going to have negative 2 plus or minus. There's going to be an imaginary answer over 2. So the plus or minus here is what's key. So again, if you get a plus bi as a root, you've got to get a minus bi as a root as well. They come in pairs. The imaginary roots come in pairs. So just to ask one more thing or to think about is the following is this. Imagine you had an equation that was x to the 9th. What are the possible types of roots you could have? You could have 9 real roots, for sure. Okay? You could have 7 real roots and 2 imaginary. Because remember, the imaginary has got to come in pairs. You can't get one imaginary. I could have 5 real roots, and I could have 4 imaginary, 2 sets of imaginary roots, right? I could have 3 real and 6 imaginary. Or finally, I could have 1 real and 8 imaginary. So a question like this might say, like, you know, a function or an equation is to the degree of 9. Is it possible to have no real roots? Well, it's not possible. You have to have a real root. Because remember, the imaginary has got to come in pairs. So you can't have 9 imaginary. You could have 2, 4, 6, 8, or 10 imaginary, but because there's 9 roots, at least one of them has to be real always. You could have 3 real, you could have 5 real, you could have 7 real, you could have all 9 of them real. Okay? So keep that in mind for a type of multiple choice kind of question.